Okay, so this is what we're talking about, initial interpretation of the system with several equations. Usually two equations, two unknowns, three equations, three unknowns, or more equations, n equations, n unknowns, but generally speaking, they don't have to match. So I could do this, and it still makes sense, like this. Okay, so it is possible. So the number of variables, I mean, real life situation, you have a number of variables that you gotta decide on, different weights to different things, for example, and then there are restrictions that they relate one quantity to another. Okay, so the number of restrictions and number of quantities don't have to match. You don't know. Okay, so like I said, that's you can easily encounter the situation when you have more equations than quantities, or vice versa. So that's why we have to look at it at the most general sense. And you can imagine what happens is if I drop one of the equations, then it is still about planes, but then instead of having 3 planes, you have 2 planes. And then right away you are in the situation when the answer cannot be that the generic situation that we like so much, that's on the left you have one solution only. Okay, so it is possible that that's not going to be the case. So, but that's not what we are concerned with right now, but rather the question becomes the matrix multiplication, which is an example here. Matrix multiplication in the most general sense. So even though we cannot visualize high dimensions than 3, but we cannot stop there. So we're going to look at matrices at the most general. So a matrix n by m is just a table of numbers with n rows and m columns. Okay. So there is a subtle point here, is that every matrix is a table, but not really every table should be looked at as a matrix. Okay, so just because you arrange numbers in a table doesn't mean that there is some point of calling it a matrix. Matrices come with algebra. So matrices will be multiplied. If whatever table that you have, numbers that you have, if there is no point of it multiplying by anything else, then it's just call it a table. Okay, just to be safe. You can call it array, whatever you want to call it, but matrix matrix algebra is what makes a matrix a matrix. Okay, a table turns into a matrix when it is subject to algebra, specifically matrix multiplication, because sometimes you can also add matrices, but that's not the determinative idea, but rather multiplication. So that's what we're looking at right now, how to multiply matrices. And the simplest example is this. Well, not the simplest, but certainly what where we came from. Multiplying a matrix by a vector, but what is a vector if not just a matrix of a particular size? So then from that point of view, a vector in Rn is an n by 1 matrix. Okay, so once again, I call it a matrix justifiably because we will be multiplying vectors, right? So then that's it fits. It fits. Unlike just a generic table of numbers, this is fine to call a vector a matrix, even though they are kind of a different of a different origin. Okay, so and then we go straight to matrix multiplication. Before we examine this closer, let's just take care of that. So what is matrix multiplication? It comes from the dot product, as we saw last time, and we just want to do it in a manner that that relies on our understanding of the dot product. Okay, so that we don't have to do it from scratch, but rather from matrix from a dot product. So that's the idea then. Interpret the dot product of vectors, say A and B, as the matrix product, without just understanding what it is, but matrix product specifically, or rather matrix multiplication, if you like, with a row, B a column. Okay, so vector, we put vectors in the form of rows and columns, but once we start thinking about vector as a matrix, that's the idea. There are two ways to do it. You can make it into a row, you can make it into a column. Okay, so and that turns out both of them are necessary. So we have thought of vectors. Remember this 1, 2, 3. We use this notation for vectors, which was simply the shortened version of a column vector. And usually, if you think of a vector as a vector, it is a column. But for the purposes of this dot product, we are thinking about multiplying them as in a different way. So as you can see, and that is crucial. It's not the same, not vice versa. So we are not interchanging them. A times B, dot product A dot B, is not the same as B dot A in that sense. Okay, so dot product is certainly the same. Well, let me make that clear. I'm not saying that it's not the same. A dot B is equal to B dot A. That's the dot product, right? But as you can see, the idea which is we have here, when we're multiplying these two vectors as matrices, a row and a column, then it's not the same. So the first one is a row, the second one is a column. So once again, say A is equal to, say, 1, 2, 3. We already saw it last time, and now we're just doing it one more time. Okay, so that's what I'm talking about. This is A, this is B. So they are, in that sense, they're vectors, but they're also matrices. So let me then correct myself here. So our vector in our n over here is an n by 1 matrix or 1 by n matrix. So both of these are legitimate interpretations, and we use one or the other. And in the case of the dot product, we use both. Okay, so the first vector 1, 2, 3 is put as a row, and the second one is a column. But then after that it's the same. So we're using the dot product, so it's 1 times 3 plus 2 times -1 plus 3 times 0. Okay, so the answer is 1. Okay, so that's the idea that we are using initially. Once again, relying on something that we already know, we know how to do dot products. See, here we go. So it is a dot, as the dot product, it is a number, which is the way I wrote it there. Let me. No. Okay. So let's compare the old. So I would have 1, 2, 3 dot product 3 -1 0, and the answer is what I just wrote: 1 times 3 plus 2 times -1 plus 3 times 0 is equal to 1. So that's the old, and now we have a new. What is the difference? And the difference is that the end result is not a number, but rather a matrix. It is a really small matrix. It's 1 by 1 matrix. Okay. So once again, this one is 1 by 3. This is 3 by 1, and the end result is 1 by 1 matrix. Okay. So that's how we're going to multiply matrices, just as we already did last time. So as you can see, row times column. Remember that is multiplying. Well, this is example, the very recent one, but there was another example where when we did multiplication, when one of the this one at the top, as you can see, our column is in fact vector xy. Okay, and then we broke it into two. I see over there. And in the next line in the middle, we broke this multiplication of matrices into two dot products. And each dot product gives you an entry in the resulting matrix. Okay, but so we try to concentrate on one at a time, not two of these simultaneously. First equation, second equation, that's where it came from, but rather just one at a time. And the result is one single number, just as the dot product is supposed to produce. Okay, so that's what we have. And in general, so that's the comparison. Okay, so I do not put a dot anymore between those two, but it is a product of two matrices. Okay, in general, how does it work out? On n by m matrix A. A and m by k, say matrix B, are multiplied. So as you can see, the dimensions have to match. Why? Why do they have to match? Because the dot product for two vectors, we only know the dot product of the vectors when these two vectors have the same dimension. So as you can see, I have both of the vectors have dimension 3. If one is 3 and the other one is 4, that's not working. They'll be missing. They won't be a match for one of the elements. So that is why every time we look at matrices, we have to, and we want to multiply them. We want to match. There's only one match, as you can see. This is okay. So the first number, remember, the first number is in the n by n expression. So, where is it? Okay, n rows, m columns. Okay, so the first number is number of rows, the number of columns. So if you look at it, then this is number of columns in A, and at the same time, it is the number of rows in B. Okay, so those two have to match. So we're looking at this one, and it is n by m, so that's my A, n by m. So what would it, n by m? Okay, so what does it mean? It means that we have n rows. This is n, and this is m. Okay, and now we match it up with, so they don't fit together well. In fact, rows match columns, so that's not a match exactly that easy to see, but as you can see, this is m. For matrix B, it is the number of rows. So this is my B, m by k, and this is k. So the point being that these are the two dimensions that are important in the sense that they have to match. The other two do not. So why do they have to match? Once again, the dimensions to carry out that dot product, we need to the length of the vectors to match. Okay, so if I pick then a row here, it will be dot multiplied by a column there. Okay, so one by one. So these are the two vectors that I extract from my two matrices, and then I do the dot product with them. The result of this multiplication gives me exactly one entry in the new matrix. Okay, so I'm multiplying A by B. This is the matrix, which is a new one, and it is A, B. The size is n by k. Okay, so once again, I could write it here. This is still k. This is still n, as you can see. So it inherits the number of rows, from matrix A, the first one, and the number of columns it inherits from the second matrix B. Okay, so these the dimensions repeat themselves. And then now what is the point to emphasize here is this. Once again, those two vectors, one row in one column, produce one single entry in the resulting matrix. So row dot, okay, let me maybe erase this since I didn't mean to. Okay, row, column, and entry. So single row, single column produce a single entry. And so as you can see, then every number in each of the either of the two matrices, every entry will appear many times, right? So it will be used many times, as many times as in how many rows does a particular value. Say I pick this one over here. In how many rows does it appear? And the answer is n. I'm sorry, m. What am I trying to say? It appears in one row, but it will be matched with how many columns. So once again, that blue number, it certainly belongs to only one row, but in matrix A, but then it will be matched up with k possible columns in B, and then they will be multiplied. So in other words, it will appear k times. Okay, so let me carry out this idea one more time. So just some made-up numbers. 2 by 3. Multiplied by, and this one has to match. So it has to have 3. So to make that point, I'll make it 3 by 3. How about I make it? It has to have 3 rows, but the number of columns is arbitrary. So how about 4? Okay, so this one is 3 by 4. Okay, so as you can see, the trick is when you write these side by side, 2 by 3, 3 by 4, you know if you're multiplying what you're going to end up with, you're going to cancel that 3 that they share and give me what's left. So I will remove these 3 that they're being shared, and the result will be 2 by 4. So it's a good idea when you actually carry out multiplication by hand. It is a good idea to have to know ahead of time how large your output matrix is. Right? Okay, so it's 2 by 4. Then I know I'm gonna carry out 8 multiplications, 8 dot products. So that's quite a lot of work. So maybe I'll just try to do less. Okay, so fill with numbers 1 0 1 1 2 negative 1 0 2 3 0 negative 1 0 0 1 1 2 1 1. Okay. Okay, so one at a time. One at a time. So let me try to extract and do it one by one. So for this entry, so this entry is first row, first column in the resulting matrix. What does it mean? It means that I will be taking first row, first column from the other two matrices. So first row, first column. And then I do the dot product. Okay, so as you can see, 1 times 1 plus 0 times negative 1 plus 1 times 0, so the answer is 1, and that's how I put 1 here. Okay, So that's all there is. That's the whole dot product multiplication of one single entry. And then you can certainly do more of this. So I don't want to do every single one of them. So let me do it separately. So how about I pick second row, third column. So in other words, this one. Okay, so once again, I identify second row from the whole thing to negative 1, 0. That's the second column. And I multiply by the third column, which is 0, 1, 1. Okay, so I'm extracting the information from my table like this. So I am ignoring the parts that I don't care about, and now I clearly see my rows, my row, my column, and so I have 2 times 0 plus negative 1 times 1 plus 0 times 1. The answer is negative 1. Okay, so that gives me one single entry. So we found 1. And we found negative 1. So and then you carry out it every time. So any questions about this? So you think you can multiply matrices based on this? Yeah. Okay. So so as long as you don't try to multiply, it is tempting when you have 2 by 2 matrices. It's tempting just to multiply them one by one, and so all you have to do is 4 multiplication. It is tempting, but you know that is simply not. That's not matrix multiplication. It is some weird table manipulation. Okay. So so we'll be using it whenever necessary. I wanna give one more example of what we just did, and that is. So we'll do it several times in the future, but I want to take a look at this one again, what you see over here, how I converted my 2 vectors here, and I converted them to, let me do it one more time, converted them to matrices and then did the multiplication, okay? Copy. Okay. Okay, so but that's not the whole story. We could what if we would flip them? So BA. So it will be 3, negative 1, 0. I will be multiplying it by 1, 2, 3. Any guess what we're going to get? What? No. Exactly. Yeah. So that is tempting to say just 1 because it was 1 on the last occasion, but interchanging matrices change the outcome. So the word for that is, remember the word for AB is equal to BA? Yes. Okay. Commutative. Well, except not anymore. Matrices are not commutative. Right. So, well, an important property. And then to confirm that, you can see if I start multiplying, this is indeed 3 by 1, and this is 1 by 3. So the answer, the matrix is 3 by 3. So you have actually 9 entries to worry about. So I have 3 by 3 like this. And so I have to do it 1 by 1. Fortunately, it is quite, you can probably easily describe what's going to happen. You have 3 entries and 3 entries. What do you do to them to get 9 numbers? Each is multiplied by each, right? So for first row, first column, I mean, if you start thinking in terms of rows and columns again, you can see the difference. So row multiplied by this column, right? Except now, what is the row in the last line? This is the row. And this is the column. Okay, so they just happens to be so short. And then you just keep multiplying, so you you have 3, 6, 9, okay, then -1, -2, -3, right? So I multiply -1 by all the 3 entries in the second vector, and then these are just zeros. Okay, so it is a 3 by 3 matrix. So as you can see, it is a very basic matrix multiplication is not commutative. Okay, and it certainly the dimensions, as you can see, both of them match, and then so both of them make sense. So it's not that you can easily have examples even sort of in a way worse than this. You can have 2 matrices that you can multiply. You flip them, and you can't multiply them anymore. So can you think of an example? Well, example probably would be easy. Say 3 by 2 multiplied by 2 by 4. Right? Well, that's pretty much what we just did, right? So you can multiply this. The result will be 3 by 4. But if I flip them, this is A and this is B, if I go with BA, what's going to happen is 2 times 4, 3 times 2. So the result is what? What? No such matrix. You cannot multiply because there is no match over here. 4 and 2. So that all of these examples suggest that things are very different for matrix multiplication than what we have seen before. But it is not entirely unheard of. It is that the word multiplication is misleading, leading you towards thinking about matrices as if it is their kind of special kind of numbers. Just like we transitions from numbers to vectors, and they have special properties, and then now even beyond that, from vectors to numbers, to matrices, and then you expect some of the properties to be preserved, and some are not. But that's really not what's happening. You can actually go back all the way to pre-calculus and see the examples of non-commutativity. The only how do you find them there? It is simply if you think of matrices the right way. The matrices are not vectors. They are not special kind of vectors, not special numbers. That's very crucial. Matrices are functions. That's where we came from. Remember, that was our interpretation of the system of equations. It was interpreted as matrix was created in order to create a function of xy. Remember, so this is to refresh your memory. Where is it? Here it is. At the bottom, we did all the work with that system of equations, created a matrix of coefficient right there at the top. But then ultimately it is a function. It takes x, that vector xy, and makes it into b. So A is a function, and that explains why it's not. You should not expect it to be commutative. For example, to think of 2 functions, even numerical functions that do not commute, is very easy. In fact, among functions it is a common occurrence that they do not commute. Say, if I have y equal f of x equal to say x squared, and I have z equal g of y equal to say not y cubed, but say doesn't really matter what it is, sine y. Okay, so the matrix multiplication is in fact is about compositions. Okay, so that we're going to explore that further, but why they're not only every matrix is a function, but also turns out that it is how we create compositions of these special functions by multiplying matrices. We'll see how that works out. But as you can see, the example of non-commutative operations are plentiful in pre-calculus. When you have 2 functions, you can create a composition, but one composition, f followed by g, not the same as g followed by a. Any 2 operations carried out consecutively, when flipped, might produce totally different result. Best example, think like polishing and painting. So you first polish, then paint, or you paint, then polish. You see the difference of results? So as long as you understand that matrices are functions ultimately, then that strange behavior that you observe wouldn't be seem as strange. So we know how to multiply matrices, and now I guess we could now multiply any matrices by any matrices. It is I like to do it kind of by hand when I actually do multiplication, like I put. I use my left hand like this and right hand like this. Okay, so I have if I have a row, one matrix here and another one there, okay, and I have to multiply a row by column. Well, if I don't want to write on top of it, this is what I do. I have a bunch of rows here and a bunch of columns there. That's the key. So like this. This row I'm multiplying by this column. Okay, so I go left, right here. So I'm progressing this way along the row on the first one, and then I'm progressing vertically in the column in the second matrix. And one by one I multiply them and write them down, and you have the result. So there will be, in the next homework, there will be a little bit of that. Is there anything matrix multiplication in the last homework? I don't think I did put anything, so it will be in the next one. Okay, but now we have to sort of take it to the next level, and do the like algebra, an actual algebra of rather than verbal description and demonstration. You want to see a verbal. You want to see actual algebra. Okay, so that makes it slightly more complicated, but that's how you handle things when you do not handle it by hand. So think about it. You probably will just, for practice, you will do this multiplication a few times just to get a hands-on experience and just to feel for this stuff. But really, if you are solving any kind of serious problem, you probably will have some kind of program, right? And to write that kind of program, you probably could figure out what to do it with this explanation, but it's better to do it now from the beginning. So how do we describe this in a more algorithmic or algebraic sense? So then we have to be careful here and then make things clear. So what is a matrix? So it's a table, but how do we represent its values? And ultimately, this is how we count things from left to right and from top to bottom. So as you can see, it is a table. It follows the XY plane, except it's upside down, unfortunately. So that's a mismatch. Remember, XY axis like this. X goes horizontal. It still does. The first parameter of our array of numbers will be go horizontally. Unfortunately, the second Y does not go up, it goes down. Okay, incidentally, exactly the way a spreadsheet works. So we're gonna take a look at that too. But this is what we're talking about. And then usually we call we put I and J, two variables, not to be confused, even though closely related are those I and J on the X, Y. Remember those two vectors? So there is a match there, even though they're two different things. So these are just integers. So if I have n by m matrix, okay, so I have then I runs from 1 to m, and J runs from 1 to n. Okay, so that's what creates an array. So in that sense, it is a function of two variables, as if. So for each pair I and J between m and n, there is a number, and we put it two subscripts I sub j, a sub I j. So once again, like you have, the notation is the same as notation for sequences. Have you seen sequences in calculus? Okay, so that's the same thing, except we have two indices. A sequence goes on one way linearly, and this one is two-dimensional. Okay, it is certainly is what we saw not long time ago. Remember when we plotted a function of two, the graph of function of two variables. Let me see, it's here somewhere. Here probably. Yeah, here it is. Right. So a table of numbers. See, these are i's. Now we can rethink this, and we can call these. So this is my matrix. The values of the matrix. It's a table. Okay. You can see how I and j runs. I's run horizontally from 1 to 19. J runs from 0. Well, it usually starts with 1. Okay. So let's start with 1. If we wanna match things, let me move and copy. So that's going to be a matrix. Okay, and so I'll start with 1 and 1 here, and once again this will be down, we go in with j, and to the right we go with I. Okay, so I runs from 1 to 20, so which makes it that's the number of columns, and the number of rows is from 1 to 19. Okay, and then by some kind of where did these numbers come from? They could come from just data, data collected somehow, and then you handling it. Or if you want to make something up, you make up some formula, a formula with formula function of two variables. So this one in particular, the way we did it was required by what we were studying. The function had to be linear, but matrix itself does not have to be anything. There is no rule how you fill this table with numbers. You can have anything you want. So let's do that. I'll put something weird here. Doesn't really matter. Squared. Doesn't matter. Just to make a point that we do not have any restrictions. So, well, could be something like that. So if you want to just see what is happening here, well, so values, it doesn't matter what values are. I usually don't even try to visualize it this way. Incidentally, I don't want to give you an impression that it is a surface, because unlike that plane that we plotted, it was actually made of infinitely many points. This one is meant to be made of how many points, that's how many numbers you see. That is the table. There is nothing hidden in between. So let me try to change the chart type to something that would match things better. Oh, this is better, I suppose. So as you can see, well, let me try again. How about, there is a way to do it. There is a chart that is, maybe this one. No. The chart that creates a bunch of, it is like, maybe this one. Come on. That's not it. No. Maybe this one. Yeah. See? Okay, so for each cell of the matrix, there is its value. That is the number that's placed there, and it is visualized as a bar, as this little column standing vertically. Okay, so the whole thing is three-dimensional, but it's not a curve. So once again, there is nothing in between those cells. You progress from one cell to the next, and there is nothing in between. So that's why it is better to visualize a matrix with columns than with some kind of a surface. Okay, so that's what the data looks like. We certainly could multiply. This is a little bit big to actually carry out any kind of multiplication. So let's just continue on with what I've been talking about, and that is how we represent things. So Aij is, well, you just saw a formula that I guess it's crucial. to understanding of what's going on. The formula is, you can see here, you see, well, let me maybe pick this one. You see the highlighted red and highlighted blue, right? These are the references to the number or the column in the row. So the fifth row, third column. Okay, so and then the entry might depend on these. So we just do the exactly same thing, except it is typically, well, this is the notation. We prefer notation of this kind. Okay, so Aij is number placed at the intersection of what? Ith row, no, ith column. So the first number is the row. Okay, let me. Okay, so I'll. I goes down. I goes down. Yeah, I goes down. G goes to the right. Sorry about that. So this is J and this is I. Yeah, definitely. So so that makes it a little bit weirder, I suppose. Yeah. Okay. But then it makes more sense. So so it's placed in the intersection of ith row and jth column. Okay. So so once again, ith row here. So you find one and you find the other, and then the result is that intersection is where it is located. I, J, and this is Ij. And then you could have, of what we just did in the spreadsheet, say you could have, as an example, Aij is equal to what I just wrote a minute ago was, what is it? I squared plus sine j plus 3. Totally made up formula, but just to make it specific, so some values are placed in each location according to some rule, and that's what the rule is. Usually there is no rule, depending on where it comes from, but probably could be just pure data, just collected data. It is in table, and that's how you will use this formula to retrieve the value rather than to place it there. Placing it, well, I mean, you need the ability to place as well. That's, for example, when you multiply two matrices. Okay, so let's come up with a formula. So so we're multiplying A by B and is equal to C. Okay, so this one Aij, and let's say this call Bjk. So two arrays of numbers depending on these parameters. I intentionally called the second parameter of the first one and the first parameter of the second parameter of the first matrix and the first parameter of the second matrix by the same letter, so that we know we're talking about the same thing. And then it's supposed to produce somehow a matrix which is designated by ik. Okay, so then we have to retrieve every necessary value from A, every necessary value from B, combine them according to our computations, and then do the dot product, and then place it at Cik. Okay, fortunately it's not that complicated. So we do one value at a time. So we fix what? I and K. So I and K are fixed, just like in that picture. We are looking for one single value to be computed, which means that we fix row, which row? Ith row in A, and jth column in B. Right? Just once again, like that picture over here. Well, let me redo it. So A and B.
Not be the kth column.
That's right. Yeah, that's right. Okay, so I column in A. So I, okay, and then jth column in B, right? This is A and this is B, and then we're supposed to produce only one entry in C. So like G, oops, G, 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 and this one. So one single entry over here. So CI, this one is C, I, K. I, K. Okay, that's K again. I did it again. So this is K. Okay, and so how we multiply them we know. So that's one row. The other row just must start multiplying, and GA runs here from 1 to what is it? I didn't identify numbers. So what? Probably. So this is N by M. This is M by. I recycled letter K, I'm afraid. So I'll put K here, but I'll have to change the index to. I don't have a good index. How about P? P. So K stands for the size of the column. Okay, so we'll finish the formula next time.